today we will discuss a structure called Metroid, and we will discuss an algorithm related to it. Metroids provide an abstraction for many problems in graph theory and in some other domains. A Metroid is a tuple where S is a set of a finite set of elements, and the script I is a collection of some of the subsets of S which satisfy certain conditions. Condition 1 is that if A is a subset of B and B belongs to I, then A also belongs to I. The second condition that this collection should satisfy is that if A and B both are members of I and the cardinality of A is no greater than the cardinality of B, and there is some element x in A minus B. That is to say, if visualized this way, then there is an element y in B minus A such that B minus y union x also belongs to I. These two conditions must be satisfied by this family of subsets of S. Here is a small example. So, I have set S containing 4 elements, and the script I, the family of subsets, contain the singletons 0, 1, 2 and 3, and these 5 additional sets containing 2 elements. Now, if you consider this set and this set, if take this as an A and this as B, then 0 belongs to A minus B. Then there is an element in B, namely 2, such that B minus 2 union 0, namely 0, 1, is also a member of this collection. The subset property is quite trivially satisfied in this case. So, this one can verify that this is an example of a Metroid. Now, there is one theorem which I will leave for you to do verify yourself, and the theorem says that the cardinality of every maximal set of I is same. By maximal set we mean those sets of I which are not properly contained in any other set of I. And the claim is that all such sets have same cardinality in a Metroid. One more thing, we will call the members of I independent sets for some historical reason. So, in our example, all the maximal sets are 0, 1, 0, 2, 0, 3, 1, 2 and 2, 3. They all of course have cardinality 2. Now, we define a weighted Metroid. A weighted Metroid is a 3 tuple S, I and a weight function, where weight function assigns weights to every member of S, where weight is a function from S to real numbers. We will accept both positive and negative numbers. Now, then the weight of any member A of I is given by sum W of x belonging to A. It is simply the sum of the weights of the elements of independent set A. Now our problem that we want to address today is to determine one of the maximal independent sets, one of the sets with largest cardinality in I, which has maximum weight. So, the problem that we want to address is to compute A maximum weight maximal independent set. Notice that this maximal refers to the cardinality of the set and this refers to the weight. Okay. So, now we are going to give a simple method, and I will not call it an algorithm yet. We will verify the correctness of a method, and then later on we will look at an example by taking an application of a Metroid method to a graph problem. So, let us take the algorithm which seems pretty trivial, a greedy algorithm to compute such a set. So, you are given a weighted Metroid in step 1. We will sort the elements of S in non-increasing order convenience, I will assume that the ordering is x1, x2, x3, where the weight of x1 is greater than or equal to weight of x2, weight of x2 is greater than or equal to weight of x3, and so on. In the second step, we take an empty set and now we iterate in the following fashion. If so, all we are doing is we start with an empty set and starting from the highest weight element, we put it in the set and check whether it is still an independent set, because we are interested in an independent set. If it is still independent, then we update A by putting that element and then move on to the next element. And finally, we return the final output A. Now, notice that in this so called algorithm, there is a step which checks whether a certain set is independent or not. Now, in general, a Metroid may not be given to you in explicit manner, and hence one does not know whether such a step is feasible to evaluate. And that is why this is not quite an algorithm in classical sense, because each step must be feasible. But if it is possible to evaluate this, to check the membership of this entity, then it becomes a meaningful algorithm. So, next thing we are going to do is try to prove that this indeed computes our object, namely the maximum weight maximal independent set. All right. So, let us start with first claim. In order to define these claims, I am going to use a certain notation. I will denote the value of A after ith iteration by AI, A subscript I. So, the final output is AN. We will say AN, which is the value of A returned in final step. So, first claim is that AN is a maximal independent set. Well, it is quite obviously an independent set, because in each step we have checked whether current A belongs to script I. So, it is obviously an independent set, but it is not clear whether it is a maximal independent set. So, let us try to prove this. Suppose AN is not a maximal independent set. Suppose AN is not maximal, then there exists a set C in I such that A n is strictly contained in C. This means that it is contained in C, but it is not equal to C. Now, since this is strictly larger than A n, then there must be some element x j in C minus A n. In the difference set, there must be an element x j. So, let us just put the picture here. This is A n and this, let us just draw this way. This is C and here is an x j. Okay. Now, let us look at all the elements of A n with index less than j. Okay. Let B be the elements of so B is a subset of A. Now, what we have decided to do is call the set A after ith iteration by AI, A subscript I. Then notice that this set from our notation B is precisely A j minus 1, because from A n we have deleted those elements which had index greater than j, greater than or equal to j. Of course, x j is not in A, so it does not matter. Then in the jth iteration, we must have tested whether A j minus 1 union x j belongs to I. Now, since x j belongs to C minus A n, J is not a member of A n. Hence, we must have found that A j minus 1 union x j does not belong to I. Yes. This is that x j does not belong to A. Hence, we must have found that this set is not in I. Now, on the other hand, but notice that A j minus 1 is a subset of A n, hence it is a subset of C, and x j is also a member of C. So, we conclude that A j minus 1 union x j is a subset of C. Now, from Metroid condition 1, from 1 A j minus 1 union x j must belong to I. So, we find a conflict here, a contradiction. Hence, it is not possible to find any element xj in this, which implies that an must be itself a maximal independent set. This is what we wanted to establish, that at least it is a maximal independent set. Next, we want to prove another useful claim, and the claim is the following. Let be not the same as an be a maximal independent set. So, I have some another maximal independent set B. Let us just draw the picture here. Of course, both of these sets have same cardinality, because we have already claimed that all maximal independent sets have same cardinality. Let S be the index, the smallest index of the elements in an minus b. Let S be the smallest index in an minus b, and T be the smallest index in b minus an. Then we want to prove, then we want to show that S is less than T. Okay. The proof of claim 2. So, what we have is set B and set an. Here we have x t, where t is the smallest index in this region, and x s, where s is the smallest index in this region. Assume the contrary, assume that t is actually less than s, and let us arrive at some kind of contradiction. Now, let C be the set of elements xi in an such that I is less than t. Okay. So, we are taking all the elements of an with index less than t. Obviously, t is not in an, so it will be always only up to t. Now, clearly, as we noticed earlier, again observe that C is a t minus 1, and we also know that C is a subset of B. Notice that all the indices in B minus A and in an minus B are greater than or equal to t. Hence, everything smaller than t must be in the common region. Hence, our particular set C must be contained in the intersection of the two. Okay. Now, we must have found that a t minus 1 union x t does not belong to I, because we rejected x t from A n. So, at this stage we must have found that this union is not in I, but what we notice is that a t minus 1 is in B. We also notice is that x t is also in B. So, we notice that a t minus 1 union x t is a subset of B, and from the first condition of Metroids, from condition 1, a t minus 1 union x t must belong to I. Once again, what we have found is there is a contradiction. Hence, our assumption must be wrong. And since S and T are distinct, the only option left is that S is less than T, strictly less than T. So, that is the objective of the second claim which we have established. Now, finally, we will prove claim, we will establish that A n is indeed a maximum weight maximal independent set. A n is a maximum weight maximal independent set. Now, to prove this, let us look at those sets which are maximum weight among the maximal independent sets. If A n is already in this, then there is nothing to prove. So, let us assume that A n is not a max weight set. So, there has to be at least one maximum weight maximal independent set in the collection. So, suppose B1, B2, Br are, these are all maximal independent sets with maximum weight. Notice that R has to be at least 1. So, let us just look at the picture here. We have A n, and then against each B1 B through Br, there is some S1 and some T1 up to Sr and Tr. this S1 is in an minus B1. It is the smallest index among them. T1 is the smallest index in B1 minus an, and we have already shown that this is the inequality. So, we will claim that the same is true with each one of these sets. Now, among all these, let me pick the largest S value. So, among these S1 through SR, without loss of generality, assume that S1 is largest. Without loss of generality, suppose we assume that S1 is the largest index. Now, look at this set B1. We have X S1 and we have X T1. Okay. So, from condition 2 of the Metroids, B prime, which is B union X S1 minus some element Xj also belongs to I, where Xj is some element in this region. So, it could be Xt1 or it could be any other element in this part. Now, since J is greater than or equal to T1, because by choice T1 was the smallest index in this region, and we have already proved that X is less than T1, X S1, S1 is less than T1. So, we have J greater than S1. Okay. So, what we notice is that the weight of this element is greater than or equal to weight of this element, because our indexing is in non-increasing fashion. So, the weight of Xj is less than or equal to weight of XS1. XS1. Hence, the weight of B prime is at least as much as the weight of B. Now, B is one of the maximum weight maximal independent set. So, we conclude that B prime is also a max weight maximal independent set. So, let us come back to this picture, and what we conclude is that the set B prime must be one of these. All right. So, the question is, what would be the corresponding Si and Ti? So, let me just plug in one set here, call it BP. We have SP here, we have TP here, and of course, that inequality holds, and let this be same as our B prime that we have calculated. Now, in our picture, xs, xt, xj, what we have done is we have deleted this and we have included xs in our B prime. Now, if you look at B prime minus an, then the smallest index in B prime minus an must be strictly larger than s. Okay, so I'll write down that since an minus b prime is actually an minus b minus xs, hence the smallest index in an minus b prime must be greater than s. Now, we had labeled our b prime as bp. Our b prime is same as bp, and the corresponding smallest indices in their complementary regions were Tp and Sp. So, from this observation we conclude that Sp is strictly larger than S. We have been saying S1, so I will call it S1. This is larger than this. Now, if you recall, the choice of S1 was based on the fact that this was the largest index in the list of SIs that we had listed there. But we now have a bigger S than S1. So, this is again a contradiction. This is absurd, and hence our assumption that an is not a max weight maximal independent set must be wrong. Hence, an must be a max weight maximal independent set. So, we have now established that the algorithm correctly computes the desired object, namely one of the maximum weight maximal independent sets. So, now here is one question for you. Suppose I want to compute the problem now is I want to compute one of the minimum weight maximal independent sets. Compute a minimum weight maximal independent set. So, the only change here is that instead of maximum I want to compute the minimum weight. So, how do we solve this problem? Now, the answer is very simple. Observe that we are free to choose negative and positive weights. Hence, we can actually invert the weights. If we replace the weights by their negation. So, suppose I define a new Metroid where the weight function is different, everything else is same. This of A is equal to minus of W of A for every A in S. We just do that and then run our algorithm to compute a maximum weight in new sense. We will get a minimum weight in the old sense. The implication of this observation is that in our algorithm, the first step where we are sorting the elements of S, for minimum weight we will have to sort in the reverse order. We will have to sort in non decreasing fashion. So, the first element will have minimum weight, next will have the next and so on. Hence, we can solve both the maximum and minimum problem. Okay, so now let us look at the time complexity of this quote unquote algorithm. Notice that we do not have the answer to the question of membership. We do not know how much would it cost. It depends on how our Metroid is represented. So, let us suppose it takes f time to determine the membership of I. If I assume f is independent of the size of the set for which we are checking the membership. In that case, the time complexity is n log n. This is because we have to do sorting. N is the total size or cardinality of S, plus in each step we do one membership check and one constant operation. So, maybe we can say this is the total cost of the for loop. So, the cost looks like this. In case f depended on the size of the set we are testing, that could happen. Then let us say the cost is f r, where r is the size of the set being tested, then this cost would look like order n log n plus some f I going from 1 to n. Notice that in ith iteration the set we are testing cannot have size greater than I. So, this would be an upper bound to the total cost of computing the set A n or the final set A. Now, what we will do is we will discuss one application of this abstract structure in graph theory and show that this simple algorithm computes a desired object in that case. As one comment that I want to make in this about this algorithm is that this is a greedy algorithm. Every time we make a decision about whether x must be in the final, xi must be in the final set or not, we do one test and then finally put this back into the set A, and we never go back on it. So the decision is made then and there. We do not wait for some other computation to make this decision whether xi should go into the set A or not. So now I am going to just introduce a problem in graph theory, and then in the next lecture we will show how this algorithm works for that problem. The problem that we will discuss in the next class is computing a spanning tree in an edge weighted graph such that the weight of the spanning tree is minimum. So suppose we are given an edge weighted graph VEW the weight of any subgraph V comma E V prime comma E prime is some WE for E belonging to E prime. So we define the weight of any subgraph as the weight, sum of the weights of the edges of that subgraph. Then we would like to know, compute a spanning tree of the given graph with a condition that the weight of that spanning tree is minimum, such that its weight is minimum. This is the problem that we would like to address in the next lecture.